Hello to AP Chem. This is Chapter 7, Atomic Structure and Periodicity. Starting off talking about the nature of light and matter. So, all light, as we know, is electromagnetic radiation. It's radiant energy that exhibits wave-like behavior and travels through space at the speed of light, assuming we're in a vacuum. This is the spectrum we're used to. This is traveling on your left from high energy over to your right, lower energy. So, pulling up a pen here. We sort of see wavelength increasing in this direction. There's our arrowhead. We can also look at frequency, which would be increasing to our left. I'm going to draw the symbol for frequency, which is the nu. It sort of looks like a V, sometimes looks like a U. But we also see blown up is the visible spectrum here. And these units, it's important we note these are in meters. Often we'll see the nanometers. And a dead giveaway is visible light in nanometers is 400 nanometers down to 700 nanometers. And you'll often see this on the AP exam, not to flummox you, but to sort of give you a little shot about making sure you understand your metric system. So the parts of the wave that we need to be familiar with in chemistry are wavelength and frequency, given by their symbols, lambda for wavelength and again nu for frequency. Wavelength is the distance between two consecutive peaks or troughs in a wave, or any two light points in a wave, and it's measured in meters. Frequency is waves per second that pass a given point in space. The units for frequency are hertz, aka the inverse of a second, aka seconds to the -1. So this is three different ways we can look at waves of different frequency and wavelength, and we notice that as we see wavelength decreasing, our frequency is increasing. And so we could say these have an inverse relationship, which is very much true. The speed of light is the definition of this inverse behavior. So speed of light is a constant in a vacuum, 3 times 10 to the 8th meters per second. The product of the frequency and the wavelength of any bit of light is always going to be this value. So just understand those particular details. Keep in mind, and this is on your AP chart, the speed of light is 2.998 times 10 to the 8th meters per second. I wrote 3 here because when we're in a multiple choice, it's 3. On an FRQ, that'll be 2.998. So here's a question. The yellow light given off by a sodium lamp has a wavelength of 589 nanometers. What's the frequency? So you should remember we can't work in nanometers, we need to work in meters. So let's call that 5.89 times 10 to the -7 meters. Tricking through that right there. And we're going to plug it into our speed light formula rearranged. And there is our value in hertz, or in cycles per second. 5.09 times 10 to the 14th cycles per second. 3 sig figs maintained, and there you have it. There it is with pretty digits and pretty units canceling. Until the early 1900s, it was believed that matter and energy were very different things. Matter was composed of particles, and energy composed of waves. In 1901, Max Planck found that when solids were heated strongly, they absorbed and emitted energy. He determined that energy can be gained or lost only in integer multiples of this value, Planck's constant, times the frequency of radiation detected. So the Planck-Einstein formula is this value. You see a delta E is equal to the number of photons given by an integer times Planck's constant, written there, and frequency. An oversimplification, not an oversimplification, and a simplification in terms of 1 bit or 1 photon, then this equation simplifies to. So this is for 1 single photon. Keep that in mind throughout this unit and for the rest of the year. This relationship shows that energy is quantized and is a function of frequency. Packets of energy are quanta, that's the plural, and then quantum, a singular. So 1 quantum is 1 packet of energy, and quanta are multiple packets. So anyways, basically, as energy increases in these increments, Okay, that's given by Planck's constant as a function of frequency. Calculate the smallest increment of energy that an object can absorb with a yellow light whose wavelength is 589 nanometers. We already did this for wavelength. Now, our formula then became the energy of the photon is equal to Planck's constant times frequency. And so first, we need to convert this value to frequency, which has happened there. And then we're going to take that value resulting here and plug it into the Planck-Einstein equation, and we get 3.37 times 10 negative 19th joules. Again, this is for one photon. The photoelectric effect was explained well by Einstein. It was discovered by Hertz, but described by Einstein. We've talked about a lot in terms of the photoelectron spectroscopy. But the principle behind it is what holds it all together. Basically, it states that light of sufficient frequency shining on a reactive metal can cause current to flow. In other words, electrons to move. They found that through studying the phenomena that frequency could change the current, and the current later became electrons moving at certain energies. This is a great image. I love this. It basically takes 3 bits of light, 700 nanometer light, a 550 nanometer light, and a 400 nanometer light, and this is frequency. And electron volts values are there for our physics kids. But essentially what you see with the longer wavelength, which would be a lower frequency light, you aren't even able to eject an electron. But with higher energy, shorter wavelength, we're able to get an electron with a certain velocity. Even higher energy, shorter wavelength, we get a velocity that's even greater. And this is potassium, and the threshold to eject an electron, a photoelectron, is 2.0 electron volts. And to spare you, we can convert that into a joules value if we want to, but in this case, it's simply an example where we're noting that increasing frequency or shortening wavelength results in greater and greater output of electrons from the surface of the metal. So the photoelectric effect helped Einstein conclude that light must exist as particles in some way, each having a given energy. And so he proposed that electromagnetic radiation can be viewed as a stream of particles called photons. And so this is sort of a combination of the Planck-Einstein formula and the speed of light formula, in which the energy of a photon can be calculated directly with those 3 bits of information: Planck's constant, speed of light, and the wavelength of light, the light input. So, and again, this would assume that the photon or the photoelectron ejected had 0 energy after being ejected from the atom. So this describes what I stated on the slide with the picture, but we have to make that assumption when we look at this formula that there's no excess energy. Special relativity is not really part of chemistry, but I like this slide, so there you have it. Read it if you like. deBroglie's equation suggests that very small particles like electrons might also display wave behavior, and he came up with the relationship known as the Broglie equation. Frequency is equal to Planck's constant divided by mass times the frequency, the velocity of the electron particle's motion. So we can apply deBroglie's equation, but it was proven in the 1920s using a beam of electrons studying diffraction and interference pattern, found that electrons behaved a lot like light. And so we have the wave nature of electrons, we have the particle nature of light, which is sort of at a threshold of where light and matter have very similar behaviors. J.J. Thomson, the discoverer of the electron, his son George won the Nobel Prize in Chemistry for this finding in the 1930s or 40s, I believe. I'm not sure how long after he discovered he actually won, but there you go. So de Broglie wavelengths are a fun finding. Is that in small objects such as electrons, de Broglie wavelengths are a big deal, but in larger objects they're not. Heavy objects, or things that we would consider things that have mass, have very short, but they do have wavelengths. For example, a 145 gram baseball thrown by a pitcher in baseball like Dallas Keuchel at 90 miles an hour has a wavelength of about 1 × 10⁻³ meters. It's a pretty short wavelength. So here we go with a neat graphic showing light as a wave phenomenon, light as a stream of photons, and the same could be said for electrons. So we can also separate light. When radiation is separated into single wavelength components, a spectrum is produced. A prism can be used to do that. We can also use a diffraction grating. And when we use white light, we'll produce a continuous spectrum, and a rainbow is a continuous spectrum. Not all light does this, though. Some emitters of light radiate only certain colors and wavelengths. This produces a bright line spectrum. When various gases, you can use pure gases like neon or nitrogen or hydrogen. When various gases at low pressures are put into glass tubes and a voltage is applied through that gas, they glow with a significant signature of colors. And if you put that light that they produce through a spectrum, through a prism, you'll get a signature pattern, bright line spectrum. And each element, and even a lot of compound gases, are unique in their pattern formed. This is one of the ways we can tell the makeup of a star that's very far away. So here's the principle of separating light. Here we have electric white light going through a slit through a prism and then producing a continuous spectrum. If you take a sample of, for example, hydrogen gas through a slit in the spectrum, you get 4 distinct bright lines, and they're found at 4 positions along the visible spectrum. Now, that doesn't mean all the spectrum is in the visible. It's just that in the visible spectrum we get 4 distinct lines. There's also a chunk of the spectrum for hydrogen in the ultraviolet range, and perhaps other parts of the spectrum. This is a graphic that shows a lot of common compounds and elements, signature diffraction patterns, and bright line spectra in their respective wavelengths. And you can see that some produce tons of lines, some produce very few. Hydrogen being one of the most notable, most consistent. Mercury is pretty consistent, or not consistent, I shouldn't say that. Fairly easy to delineate just a few lines. A lot of this study was done with hydrogen, and Niels Bohr found that absorption of light and emissions of light by hydrogen atoms corresponded to energy changes of electrons within the atom. Bohr proposed that the electron in hydrogen travels only in certain allowed orbits. And this goes back to what we learned in introductory chemistry about how with that one single electron orbiting hydrogen, when given certain packets of energy, is able to go to distinct positions. Here, here, or here, or here, and this is what we see in the visible spectrum. This is an oversimplification, but it's only able to go to those positions, not allowed to go, or not able to go to other positions. So we talk about the term ground state. That's the lowest energy level of an electron, and an excited state is an electron that's gained a packet of energy and moved to a higher energy state. And it's important to understand that an excited state for an electron is So here are the excitations we see. There's 3 of them, 3 different hydrogen excitations, and energy increasing throughout. You have ground state here, you have here, 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 for 4 total states. Very quickly, and not really relevant to AP Chem, but interesting nonetheless, is the wave mechanical model. During the discovery of quantum and all things about it, Schrödinger and deBroglie worked on a wave mechanical model. The electron is seen as a standing wave as opposed to a traveling wave, like more like a vibrating guitar instead of an ocean wave, and did lots of studies to describe the electron in such a manner. The orbital in an atom is the place where there's a 90% probability of finding an electron, where the wave function is part of that. And Schrödinger's equations yields as many wave functions and associated energies as an electron can possibly obtain. So this goes into Heisenberg's principle, is it's impossible to know both the position and the momentum of a particle in a given time. It's negligible in things you can hold and see, but it's important with things like an electron. And although uncertainty is assured, 90% probability of finding an electron in that space. It's not a container. Without the electron, there is no orbital. So here's that graphic where there's a probability of finding an electron versus distance from the nucleus, and there's that uncertain dot. And that's it. We'll continue with our next video, electron arrangement, in a very short amount of time.